Hello, and welcome to The Sleepy Scientist. If you're ready to unwind and explore something fascinating, you've come to the right place. Before we begin our journey into the strange science of sound, don't forget to like, subscribe, and click the notification bell so you never miss a moment of our relaxing explorations. And while you're here, we'd love to know, where are you watching or listening from? Is it the hum of the city, the peaceful sounds of nature, or perhaps somewhere quieter still? Wherever you are, sound is all around us, shaping the world in ways we may not always notice. Tonight, we'll delve into the mysterious, invisible force that is sound. From the gentle rustle of a leaf to the booming roar of thunder, sound surrounds us. But how much do we really understand about it? How does it travel through the air? What makes a sound high or low? And what hidden power does it hold over us? So sit back, relax, and join us as we journey through the fascinating and sometimes strange world of sound. Let's start with the basics and discover why sound isn't just something we hear, but something we experience in ways that shape every moment of our lives. Sound begins with movement, not dramatic movement, not something you can easily see, but motion at a scale so small it often escapes notice. A string trembles, a vocal cord gently pulses, a speaker cone shifts back and forth by tiny distances. That subtle motion is enough to set the surrounding world into motion as well. At its most fundamental level, sound is a mechanical wave. The word mechanical is important. It means that sound requires a medium, which is a substance made of particles, in order to travel. Air can serve as a medium. Water can serve as a medium. Solid materials like wood, steel, or even bone can serve as a medium. Without particles to push against and pull away from, sound simply cannot propagate. This is why sound cannot travel through a vacuum. In outer space, where there are vast regions with almost no particles at all, there is no material to compress or expand. Light can cross that emptiness because light is an electromagnetic wave and does not require a material medium. Sound, however, depends entirely on matter. No particles, no sound. It is as simple and as profound as that. So how does it begin? Imagine a guitar string. When plucked, it vibrates. That vibration is a rapid back and forth motion around its resting position. As the string moves forward, it pushes into the air molecules in front of it. Those air molecules, which are already in constant motion due to thermal energy, are forced slightly closer together. This region of increased density is called a compression. When the string swings back in the opposite direction, it leaves a region where air molecules are slightly more spread out. That region is known as a rarefaction. Compression and rarefaction alternate in a repeating pattern, moving outward from the vibrating source. This pattern of alternating high and low pressure travels through the medium as a longitudinal wave. In a longitudinal wave, the motion of the particles is parallel to the direction the wave itself travels. The particles do not travel across the room from the guitar to your ear. Instead, they oscillate back and forth in place, passing the disturbance along like a carefully coordinated ripple. This is an important distinction. Sound is not a stream of particles flying from source to listener. It is a transfer of energy through organized vibration. The rate at which these compressions and rarefactions repeat is known as frequency. Frequency describes how many complete cycles of compression and rarefaction occur in 1 second. A higher frequency means more cycles per second. A lower frequency means fewer cycles per second. Although frequency is often measured in a unit called hertz, it can simply be understood as cycles per second. When a source vibrates slowly, it produces a low-frequency wave. When it vibrates rapidly, it produces a high-frequency wave. This difference in frequency is what eventually allows the human brain to interpret sounds as low or high in pitch, though that perception will come later. For now, it is enough to understand that frequency is a measurable physical property of a wave, tied directly to how quickly the source vibrates. The distance between one compression and the next is called wavelength. Wavelength depends on both the frequency of the vibration and the speed at which sound travels through the medium. In air at room temperature, sound travels at roughly 340 meters per second. That means a low-frequency sound with fewer cycles per second will have a longer wavelength, while a high-frequency sound will have a shorter wavelength. The speed of sound itself depends on the properties of the medium. In general, sound travels faster in solids than in liquids, and faster in liquids than in gases. This might seem surprising at first, but it makes sense when considering how closely packed the particles are. In a solid, particles are tightly bound and can transfer vibrational energy quickly. In air, particles are much farther apart, so the energy transfer takes slightly longer. This principle explains why placing an ear against a railway track allows someone to hear an approaching train before it becomes audible through the air. The sound energy moves more efficiently through the solid steel than through the surrounding gas. Sound differs fundamentally from light in another important way. Light is an electromagnetic wave composed of oscillating electric and magnetic fields. It does not require a medium and can travel through empty space at a speed of approximately 300,000 kilometers per second. Sound, by contrast, is far slower and entirely dependent on matter. It is governed by the mechanical properties of the material it moves through, such as density and elasticity. Elasticity plays a crucial role. A medium must be able to return to its original shape after being disturbed. This restoring force allows compressions and rarefactions to continue propagating. Without elasticity, energy would simply dissipate without forming a wave. The scientific understanding of sound did not emerge all at once. Early thinkers observed echoes, musical tones, and vibrations, but the mechanisms were not immediately clear. In the 17th century, Robert Hooke conducted experiments that helped clarify the connection between vibration and pitch. By observing how the frequency of a vibrating object changed the sound it produced, Hooke contributed to the growing recognition that sound was intimately linked to mechanical motion. Later scientists built upon this foundation. They refined measurements of wave speed, studied resonance, and developed mathematical descriptions of wave behavior. But even in those early investigations, the essential idea was already forming. Sound is vibration transmitted through matter. There is something quietly elegant about this. Every whisper, every clap of thunder, every distant footstep is a story of particles nudging one another in perfect sequence. The air in a room becomes a temporary messenger, carrying organized pulses of pressure from one place to another. Even the human voice follows the same principle. Air from the lungs passes through the larynx, causing the vocal cords to vibrate. Those vibrations shape the surrounding air into patterns of compression and rarefaction. The tongue, lips, and mouth then sculpt those patterns into recognizable speech. Language itself is built on carefully controlled mechanical waves. It is easy to think of sound as something intangible, something fleeting, yet it is rooted in the very physical reality of matter. It is pressure and motion, it is density and elasticity, it is energy traveling through contact. And perhaps most intriguingly, sound reveals that the world is rarely still. Even in apparent quiet, molecules are in motion. Materials respond to the slightest disturbance. Energy transfers continuously in ways that remain invisible to the eye. So when a leaf rustles or a distant door closes, what is really happening is not magic, and not mystery in the supernatural sense. It is physics. It is particles moving in disciplined patterns. It is a mechanical wave, dependent on substance, shaped by vibration, carried by compression and rarefaction across the medium that surrounds you at every moment. Sound is not merely something heard, it is motion made meaningful. Once sound begins as vibration, it settles into patterns that physics can describe with remarkable precision. Every sound wave carries 4 fundamental properties that shape how it behaves and how it is experienced: frequency, amplitude, wavelength, and speed. These are not abstract ideas. They are measurable, physical characteristics that define what the wave is doing as it moves through a medium. Frequency describes how many complete cycles of compression and rarefaction occur in 1 second. If a source vibrates slowly, producing fewer cycles per second, the frequency is low. If it vibrates rapidly, producing many cycles per second, the frequency is high. Frequency is directly determined by the motion of the source itself. A tuning fork vibrating at steady rate produces a steady frequency. A human voice constantly shifts frequency as vocal cords tighten or relax. Amplitude describes something different. While frequency tells you how often the air is compressed and expanded, amplitude tells you how strongly it is compressed and expanded. In simple terms, amplitude measures the size of the pressure variation. A larger amplitude means greater differences between compression and rarefaction. Greater pressure differences carry more energy. More energy generally results in a louder perceived sound. It is helpful to imagine two waves with the same frequency but different amplitudes. They oscillate at the same rate, but one pushes the air molecules much harder. The rhythm is identical, yet the strength differs. One might be a gentle whisper, the other might be a shout. Wavelength is closely connected to frequency and speed. Wavelength is the physical distance between successive compressions or between successive rarefactions. If a sound has a high frequency, meaning many cycles per second, and it travels at a fixed speed, the compressions must be closer together. This produces a shorter wavelength. If the frequency is low, the compressions are spaced farther apart, producing a longer wavelength. The relationship between speed, frequency, and wavelength is one of the most important principles in wave physics. It can be expressed clearly as wave speed equals frequency multiplied by wavelength. When spoken aloud, that principle is simple and elegant. If the speed of sound in a given medium is constant, increasing the frequency will decrease the wavelength. Decreasing the frequency will increase the wavelength. The three quantities are bound together. Speed itself is determined by the properties of the medium. In air at a comfortable room temperature, sound travels at roughly 340 meters per second. That is fast enough to cross a football field in less than a second, yet slow enough that lightning can be seen before thunder is heard. In water, sound moves at roughly 4 times that speed. In steel, it travels even faster. Why does this happen? The speed of sound depends primarily on two physical properties: density and elasticity. Density refers to how closely packed the particles are. Elasticity refers to how strongly the medium resists deformation and returns to its original shape. In general, greater elasticity allows vibrations to be transmitted more quickly, while greater density can slow them down. The balance between these two properties determines the wave speed. Temperature also plays a role, particularly in gases like air. As temperature increases, air molecules move more rapidly. Because they are already in motion and collide more energetically, they can transfer vibrational disturbances more efficiently. As a result, sound travels faster in warmer air than in colder air. On a cold winter evening, sound waves move slightly more slowly than they would on a warm summer afternoon. These changes are subtle but measurable. Scientists have long relied on careful experiments to determine these relationships. In the 19th century, physicists refined techniques for measuring the speed of sound under controlled conditions. Their findings confirm that wave speed is not a universal constant for sound. It depends entirely on the medium and its state. Most sound waves in air are longitudinal waves. In a longitudinal wave, the motion of the particles is parallel to the direction of wave travel. The particles oscillate back and forth along the same line that the wave propagates. Compressions and rarefactions move forward, even though individual particles remain near their original positions. There is another type of wave known as a transverse wave. In a transverse wave, the motion of the particles is perpendicular to the direction of wave travel. Light waves are transverse electromagnetic waves. Ocean surface waves are largely transverse as well. In solids, certain forms of sound can propagate as transverse mechanical waves, because solid materials can support shear forces. Gases and liquids, however, cannot sustain those sideways restoring forces, so sound in air and water is primarily longitudinal. As sound waves travel through air, they interact constantly with their environment. They reflect off surfaces, refract when passing through regions of different temperature or density, and diffract around obstacles. Reflection produces echoes. Refraction bends sound waves when they move through air layers at different temperatures. Diffraction allows sound to spread out after passing through an opening or around a barrier. Absorption also plays a significant role. When sound waves encounter soft materials like fabric, foam, or carpet, part of their energy is converted into heat through friction at the microscopic level. This reduces the amplitude of the wave and dampens the sound. Hard, smooth surfaces like stone or glass reflect more sound energy, which is why empty rooms can feel echoing and lively. One of the most intriguing phenomena related to wave behavior was described in 1842 by Christian Doppler. Doppler proposed that the observed frequency of a wave depends on the relative motion between the source and the observer. When a sound source moves toward an observer, the compressions are packed closer together, increasing the observed frequency. When it moves away, the compressions are stretched farther apart, lowering the observed frequency. This effect, now known as the Doppler effect, can be heard whenever an ambulance passes by. The siren sounds higher in pitch as it approaches and lower as it recedes. The source itself may be producing a constant frequency, but the motion alters how the wavefronts reach the listener. The Doppler effect applies not only to sound but also to light and other waves. In astronomy, it is used to measure the motion of stars and galaxies, yet its conceptual foundation was rooted in careful thinking about sound waves moving through air. The physics of sound waves reveal something quietly reassuring. These invisible vibrations obey consistent, measurable laws. Frequency, amplitude, wavelength, and speed are not mysterious forces. They are interconnected properties governed by the mechanical behavior of matter, and yet within those laws lies endless variety. A single change in frequency can shift a tone from deep and resonant to bright and piercing. A small increase in amplitude can transform a murmur into a roar. A slight variation in temperature can subtly alter the speed at which vibrations move through the atmosphere. Every sound you hear is shaped by these principles. The rustle of leaves, the hum of distant traffic, the rhythm of breathing in a quiet room, all of it arises from particles oscillating in orderly patterns. The physics may be precise, but the experience remains deeply human. Sound waves move through air as organized disturbances, guided by elasticity, constrained by density, influenced by temperature, and described by clear mathematical relationships. They are invisible structures built from motion and pressure, unfolding second by second around you, and once you understand their properties, even the simplest sound becomes a small demonstration of the laws that quietly govern the physical world. Sound never travels alone. It always depends on the character of the material carrying it. The same vibration can behave very differently depending on whether it moves through air, water, or solid matter. The medium is not just a passive pathway. It shapes the speed, strength, and reach of the wave itself. In air, sound travels as a sequence of compressions and rarefactions passing from molecule to molecule. The molecules of air are relatively far apart compared to those in liquids and solids. Because of this spacing, energy transfer from one particle to the next takes a small but measurable amount of time. At a comfortable room temperature, sound moves through air at roughly 340 meters per second. That is fast enough to seem immediate in everyday life, yet slow enough that distant thunder lags behind a flash of lightning. Water tells a different story. In liquid water, molecules are packed much closer together than in air. They are still free to move, but they remain in much tighter contact. This closeness allows vibrational energy to pass more quickly from particle to particle. As a result, sound travels through water at roughly 1,500 meters per second, more than 4 times faster than in air. This difference explains why underwater sounds can seem startlingly efficient. Two stones struck together beneath the surface can be heard over long distances. Marine mammals take full advantage of this property. Whales, particularly species such as blue whales and humpback whales, produce low-frequency calls that can travel for hundreds or even thousands of kilometers across the ocean. These calls propagate efficiently because water transmits low-frequency sound with relatively little energy loss. Low-frequency waves have long wavelengths, and long wavelengths are less easily absorbed or scattered by obstacles. In the vast, open environment of the ocean, these deep, resonant calls can move across entire basins. It is communication on a planetary scale, guided entirely by the physical properties of the medium. Solid materials amplify this effect even further. In solids such as steel or granite, particles are tightly bound within structured lattices. When one particle vibrates, it transfers energy quickly through strong intermolecular forces. Sound waves can move through steel at speeds of roughly 5,000 meters per second or more. The exact value depends on the specific material and its elasticity, but the principle remains consistent. The stiffer and more elastic the material, the faster the wave tends to travel. Elasticity is crucial here. A medium must resist deformation and then restore itself in order to sustain wave motion. The stronger that restoring force, the more efficiently the energy moves forward. Density also plays a role, but it interacts with elasticity in a subtle balance. A very dense material may slow wave motion if it lacks sufficient stiffness. What ultimately determines wave speed is the ratio between the medium's elastic properties and its density. This relationship can be expressed clearly as wave speed equals the square root of elasticity divided by density. When spoken aloud, that relationship describes how tightly bound particles and mass distribution combine to shape the motion of sound. Another concept that becomes important when comparing different media is acoustic impedance. Acoustic impedance measures how much resistance a medium provides to the passage of a sound wave. It depends on both the density of the material and the speed of sound within it. When sound encounters a boundary between two materials with very different acoustic impedance, part of the wave is reflected and part is transmitted. This principle explains why voices echo in large empty halls. The sound waves strike hard surfaces with high impedance differences and reflect back into the room. It also explains why underwater sounds do not easily pass into the air above. Water and air have very different acoustic impedance values. When a sound wave travelling in water reaches the surface, much of its energy reflects back downward rather than crossing into the air. Temperature further influences how sound travels, particularly in gases. As temperature rises, air molecules move faster due to increased kinetic energy. Faster molecular motion allows compressions to be passed along more quickly, increasing the speed of sound. On a warm day, sound waves travel slightly faster than on a cold one. Temperature gradients can also bend sound waves through a process called refraction. If the air near the ground is cooler than the air above it, sound waves may curve upward. Under different conditions, they may curve downward. This bending effect can cause distant noises to seem unusually loud or strangely faint depending on atmospheric conditions. Pressure too affects sound propagation, though in gases its influence is closely tied to temperature. At constant temperature, increasing pressure increases density, but it also proportionally increases elasticity. These effects balance in such a way that, for ideal gases, the speed of sound depends primarily on temperature rather than pressure alone. In liquids and solids, pressure can influence elasticity more directly, slightly altering wave speed. In the deep ocean, where pressure increases dramatically with depth, sound speed varies in complex ways depending on temperature, salinity, and pressure together. Oceanographers study these variations carefully because they affect how sonar systems operate and how marine life communicates. Understanding how sound interacts with materials has practical applications in architecture and engineering. Soundproofing relies on controlling reflection, absorption, and transmission. Heavy materials with high density can block sound by reflecting or absorbing its energy. Soft, porous materials convert vibrational energy into small amounts of heat through friction within their fibers. Double-pane windows, insulated walls, and specialized acoustic panels are designed to reduce sound transmission by managing impedance differences and damping vibrations. In recording studios, carefully arranged surfaces prevent unwanted reflections and standing waves. The goal is not silence, but control. The travel of sound through different materials also explains why placing an ear against a wooden door can make distant footsteps seem clearer. The solid structure conducts vibrational energy more efficiently than air. It is a simple demonstration of wave transmission through a denser medium. Even within a single material, sound does not move uniformly. Obstacles scatter waves. Irregular surfaces diffuse them. Some frequencies are absorbed more readily than others. High-frequency waves, with shorter wavelengths, are more easily scattered by small objects. Low-frequency waves, with longer wavelengths, bend around barriers more effectively. This is why deep bass notes can pass through walls more easily than sharp, high-pitched sounds. Every environment becomes a unique acoustic landscape shaped by material composition, temperature, and geometry. A cathedral, with its stone walls and vaulted ceilings, creates long reverberation times. A forest, filled with irregular surfaces and soft foliage, absorbs and diffuses sound, producing a more subdued acoustic character. In the ocean depths, whales rely on the efficient propagation of low-frequency sound to maintain contact across vast distances. In cities, engineers design materials to prevent noise pollution from disrupting daily life. In laboratories, researchers measure acoustic impedance and wave speed with precision instruments, refining the understanding of how matter carries vibration. Sound is never isolated from its surroundings. It is shaped, redirected, absorbed, and transformed by every surface it encounters. Its journey depends entirely on the properties of the medium that carries it. Air, water, and solid matter each offer different pathways for vibrational energy. Each imposes its own constraints and advantages, and through it all, the same fundamental principle remains steady. Sound is energy traveling through contact, guided by elasticity, moderated by density, and sculpted by the environment through which it moves. Every whisper and every distant echo is therefore not just a simple vibration, but a conversation between motion and matter. If sound is vibration moving through matter, then frequency is the rhythm of that vibration. Frequency describes how many complete cycles of compression and rarefaction occur in 1 second. It is a precise physical quantity. If a source vibrates slowly, producing only a few cycles per second, the frequency is low. If it vibrates rapidly, producing many cycles per second, the frequency is high. The vibrating object determines this rate directly. A large drumhead tends to vibrate more slowly. A small metal string under tension can vibrate extremely quickly. But frequency alone is not what you experience. What you perceive is pitch. Pitch is the psychological interpretation of frequency by the human brain. It is how frequency feels to the mind. When frequency increases, pitch is perceived as higher. When frequency decreases, pitch is perceived as lower. A deep bass note has a low frequency and is experienced as low in pitch. A sharp whistle has a high frequency and is experienced as high in pitch. This relationship between frequency and pitch is not merely poetic. It is grounded in the mechanics of the inner ear. Inside the cochlea, a spiral-shaped structure filled with fluid, there is a flexible membrane called the basilar membrane. Different regions of this membrane respond to different frequencies. Low frequencies stimulate one end, high frequencies stimulate the other. The position of stimulation determines how the brain interprets pitch. The German scientist Hermann von Helmholtz devoted much of the 19th century to studying this relationship between physical vibration and human perception. In 1863, he published a detailed analysis of tone sensation, exploring how complex sounds could be broken into simpler frequency components. Helmholtz proposed that the ear performs a kind of natural frequency analysis, detecting individual vibration rates and assembling them into the rich experience of sound. Modern auditory physiology has refined his ideas, but the core insight remains powerful. The ear is not simply detecting noise, it is measuring frequency patterns with remarkable sensitivity. The range of frequencies that the average human ear can detect is broad but not limitless. In young, healthy individuals, hearing typically extends from about 20 cycles per second to about 20,000 cycles per second. Frequencies below 20 cycles per second are called infrasonic. Frequencies above 20,000 cycles per second are called ultrasonic. It is worth pausing on those boundaries. 20 cycles per second is extremely slow in acoustic terms. A sound at that frequency produces long, rolling pressure waves with large wavelengths. These vibrations can sometimes be felt as much as heard. Deep rumbling thunder or distant explosions may approach this lower edge of hearing. At the upper end, 20,000 cycles per second is an astonishingly rapid vibration. Air molecules are being compressed and rarefied 20,000 times every second. Yet the ear, at least in youth, can register those oscillations as distinct tones. With age, the upper limit of hearing often declines. High-frequency hair cells within the cochlea are more vulnerable to damage from noise exposure and biological aging. As a result, many adults gradually lose sensitivity to the highest frequencies. This process is known as presbycusis, or age-related hearing loss. Beyond the human range, sound continues to exist whether it is heard or not. Infrasound, which lies below the lower limit of human hearing, plays a role in both nature and technology. Large natural events such as volcanic eruptions, earthquakes, and severe storms generate infrasonic waves that can travel across continents. Because low-frequency waves have long wavelengths, they can propagate efficiently over long distances with relatively little attenuation. Some animals appear capable of detecting infrasound. Elephants, for example, communicate using low-frequency calls that may extend into the infrasonic range. These calls can travel across several kilometers of savanna, allowing distant members of a herd to remain in contact. The physical principle is simple. Long wavelengths bend around obstacles and maintain coherence over distance. Ultrasound, on the other hand, lies above the upper limit of human hearing. Bats use ultrasonic calls for echolocation. They emit high-frequency pulses and listen for the returning echoes, allowing them to construct a detailed acoustic map of their surroundings. Because ultrasonic waves have short wavelengths, they can reflect off small objects such as insects. This makes them ideal for precise navigation and hunting in darkness. Humans have also learned to harness ultrasound. In medical imaging, ultrasound waves are transmitted into the body and reflected back from internal structures. By measuring the timing and intensity of these reflections, clinicians can create images of organs, blood flow, and developing fetuses. The underlying mechanism is straightforward wave reflection and transmission, governed by differences in acoustic impedance between tissues. Industrial applications also rely on ultrasonic testing to detect cracks or flaws within materials. High-frequency sound waves penetrate metal components, and their reflections reveal hidden structural weaknesses. The same physics that guides a bat through the night can also safeguard an aircraft engine. The perception of pitch itself is more complex than frequency alone might suggest. While frequency is the primary determinant, amplitude and harmonic structure also influence how a sound is interpreted. Musical instruments rarely produce a single pure frequency. Instead, they generate a fundamental frequency accompanied by higher frequency harmonics. These harmonics shape the timbre, or tonal colour, of the sound. Helmholtz studied these harmonic relationships in depth. He demonstrated that complex tones could be decomposed into simpler sinusoidal components, each with its own frequency. This insight later influenced the development of Fourier analysis in acoustics and signal processing. The ear, remarkably, performs a similar decomposition in real time. Different regions of the basilar membrane resonate in response to different frequencies, effectively separating components before sending signals along the auditory nerve to the brain. There is something quietly extraordinary about this arrangement. Air pressure oscillations, invisible and intangible, are translated into electrical signals. Those signals are interpreted as melody, speech, warning, comfort, or alarm. The brain assigns meaning to vibration. And yet, beneath the poetry of music and language, the mechanism remains rooted in physics. Frequency determines how rapidly matter oscillates. The cochlea responds selectively to that rate. The brain constructs pitch from patterns of neural activity. Low-frequency waves roll through the world with long strides. High-frequency waves flutter with rapid precision. Between roughly 20 and 20,000 cycles per second lies the band of vibration that most humans call sound. Beyond that band, silence to human ears may still carry information for other species or for sensitive instruments. So when a tone rises or falls, when a note feels deep and resonant or bright and piercing, what is truly shifting is the rate at which air molecules compress and expand. Frequency changes, pitch follows. The experience may feel emotional, even mysterious, but its foundation is steady and measurable. Vibrations move, the ear responds, the brain interprets. And in that quiet exchange between physics and perception, the invisible rhythm of the world becomes something that can be heard. There is a moment that almost everyone has experienced. An ambulance approaches in the distance. The siren sounds sharp and high as it comes closer. Then, as it passes and begins to move away, the pitch seems to drop instantly, becoming lower and stretched. The source of the sound has not changed its tone. The siren continues to produce the same frequency. Yet what reaches your ears is different. This shifting of frequency due to motion is known as the Doppler effect. The Doppler effect occurs whenever there is relative motion between a wave source and an observer. If the source moves toward the observer, the sound waves are compressed in the direction of motion. If the source moves away, the waves are stretched out behind it. The physical vibration rate of the source remains constant, but the spacing between successive wavefronts changes depending on motion. When wavefronts are compressed, their wavelength becomes shorter. Because wave speed in air remains approximately constant under steady conditions, a shorter wavelength means a higher observed frequency. A higher frequency is perceived as a higher pitch. When wavefronts are stretched, the wavelength becomes longer. A longer wavelength produces a lower observed frequency, which is heard as a lower pitch. The effect depends entirely on relative motion. If you are moving toward a stationary sound source, you would also perceive a higher frequency. If you are moving away, you would hear a lower frequency. It is the closing or increasing distance between wavefronts and observer that determines the shift. Christian Doppler first described this phenomenon in 1842. In his original paper, he proposed that the colour of light from stars might shift if the stars were moving relative to Earth. Although his early astronomical ideas required refinement, his principle was sound. Wave frequency changes when there is relative motion between source and observer. The physics is straightforward but powerful. Imagine a source producing a steady tone. Each compression leaves the source at regular time intervals. If the source is stationary, those compressions are evenly spaced in all directions. But if the source begins to move forward, each new compression is emitted from a slightly advanced position. The compressions in front become closer together. Behind the source, they become more widely spaced. The wave speed in the medium does not change simply because the source is moving. The speed of sound in air is determined by temperature and the physical properties of the air itself. What changes is the spacing between wavefronts. That change in spacing alters the wavelength. Because frequency equals wave speed divided by wavelength, altering wavelength alters observed frequency. This relationship can be described clearly as observed frequency equals emitted frequency multiplied by wave speed divided by wave speed plus or minus source velocity. When spoken aloud, the meaning is simple. If the source moves toward the observer, the denominator becomes smaller, increasing the observed frequency. If the source moves away, the denominator becomes larger, decreasing the observed frequency. In everyday life, the Doppler effect is most noticeable with vehicles. A passing train whistle, a racing motorcycle, or an emergency siren all reveal the shift clearly. The transition from higher to lower pitch occurs at the moment the source passes the observer. It is a smooth but unmistakable change. The effect is not limited to dramatic speeds. Even modest motion can produce measurable frequency shifts. In fact, the Doppler effect has become one of the most important tools in modern science. In medical imaging, particularly in Doppler ultrasound, the principle is used to measure blood flow. An ultrasound device emits high-frequency sound waves into the body. These waves reflect off moving blood cells within vessels. If the blood cells are moving toward the probe, the reflected frequency is slightly higher than the emitted frequency. If they are moving away, the reflected frequency is slightly lower. By measuring this frequency shift precisely, clinicians can determine the speed and direction of blood flow. This allows physicians to detect blockages, assess heart function, and monitor circulation in a non-invasive way. The sound waves used are ultrasonic, far above the range of human hearing, but the physics is identical to that of an ambulance siren. Astronomy provides an even grander application. Although sound itself cannot travel through the vacuum of space, light behaves as a wave and also exhibits a Doppler shift. When a star moves toward Earth, the wavelengths of its emitted light become slightly compressed, shifting toward the blue end of the spectrum. When it moves away, the wavelengths are stretched, shifting toward the red end. This phenomenon is called redshift and blue shift. By analysing the spectral lines of starlight, astronomers can measure these shifts with remarkable precision. From them, they calculate the velocity of stars and galaxies relative to Earth. Observations of widespread redshift in distant galaxies provided crucial evidence for the expansion of the universe, a discovery associated with astronomers such as Edwin Hubble in the early 20th century. The same principle that alters the pitch of a passing siren helps reveal the motion of entire galaxies billions of light-years away. The Doppler effect also has applications in meteorology. Weather radar systems emit microwave signals and measure frequency shifts in the reflected waves from moving raindrops. This allows meteorologists to detect wind patterns, rotation within storms, and potential tornado formation. Motion leaves a signature in frequency. One of the reasons the Doppler effect is so significant is that it allows motion to be measured without direct contact. It provides a way to determine velocity at a distance. Instead of tracking an object's position over time, scientists analyse how wave frequency has changed. At its heart, the Doppler effect is a geometric consequence of motion. Waves emitted at steady intervals are redistributed in space when the source moves. The physical wave speed remains determined by the medium. The emitted frequency remains determined by the source. Yet the observer receives a pattern altered by relative motion. There is something quietly elegant about this. Motion reshapes perception without altering the original vibration. The wave itself remains consistent in its own frame of reference. Only the spacing of its arrival changes. Christian Doppler could not have predicted the full reach of his insight. His original proposal, presented in the mid-19th century, faced skepticism and required experimental confirmation. Over time, careful laboratory work verified the effect for sound. Later developments extended it to light and electromagnetic waves. Today, the Doppler effect stands as one of the foundational principles of wave physics. It bridges acoustics, medicine, astronomy, and atmospheric science. It connects the sound of a siren on a quiet street to the expansion of the cosmos. And once you become aware of it, the world sounds slightly different. A rising pitch is no longer just a tone. It is evidence of approach. A falling pitch marks departure. The shift is not mysterious. It is geometry in motion, frequency responding to relative speed. Every time a sound source moves, the air reorganizes the pattern of compressions reaching your ear. The vibration itself remains steady, but motion reshapes its delivery. In that subtle shift from high to low, physics reveals itself again, quietly embedded in everyday experience. Sound may begin as vibration in the air, but hearing begins with architecture. The human ear is not a simple opening on the side of the head. It is a layered system of mechanical and biological engineering, shaped to capture pressure waves, amplify them, translate them into electrical language, and deliver them to the brain with extraordinary precision. The outer ear is the first structure involved. The visible portion, called the pinna or auricle, is made of cartilage covered in skin. Its curved ridges are not decorative. They help collect sound waves and subtly shape them before they enter the ear canal. The pinna also assists in determining the direction of sound, especially whether it is coming from above, below, or behind. Sound waves travel down the external auditory canal, a narrow passage leading inward. At the end of this canal sits the tympanic membrane, more commonly known as the eardrum. This thin membrane marks the boundary between the outer ear and the middle ear. When sound waves reach it, the alternating compressions and rarefactions cause it to vibrate. Those vibrations are passed to the middle ear, which contains 3 of the smallest bones in the human body. These bones are the malleus, the incus, and the stapes. Their names mean hammer, anvil, and stirrup, reflecting their shapes. Together they form the ossicular chain. The purpose of these bones is amplification. Air is a relatively low-density medium. The inner ear, however, is filled with fluid, which is much denser. If sound waves in air struck fluid directly, much of their energy would reflect away due to differences in acoustic impedance. The ossicles solve this problem by increasing pressure before the vibration enters the fluid-filled inner ear. They do this in 2 ways. First, they concentrate force from the relatively large surface area of the eardrum onto the much smaller surface area of the oval window, which is the membrane leading into the inner ear. Second, they act as a lever system, increasing the force of vibration. This mechanical advantage allows efficient transmission of energy from air to fluid. Beyond the oval window lies the inner ear, and within it, one of the most intricate structures in the body, the cochlea. The cochlea is a spiral-shaped, fluid-filled organ resembling a small snail shell. Inside the cochlea runs the basilar membrane, a flexible strip that varies in stiffness and width along its length. At one end, near the base, it is narrow and stiff. At the other end, near the apex, it is wider and more flexible. When the stapes pushes against the oval window, it creates pressure waves in the cochlear fluid. These waves travel along the basilar membrane, causing different regions to vibrate depending on frequency. High-frequency sounds create maximum displacement near the stiff base. Low-frequency sounds travel further along and peak near the flexible apex. This organization is called tonotopic mapping. Different locations correspond to different frequencies. The ear, in effect, performs a mechanical frequency analysis. The scientist Georg von Bekezy played a pivotal role in uncovering how this works. In the mid-20th century, von Bekezy conducted detailed experiments on the motion of the basilar membrane. He demonstrated that sound waves travelling through the cochlea create what is known as a travelling wave along the membrane, with peak vibration occurring at frequency-specific locations. For this work in auditory physiology, he was awarded the Nobel Prize in 1961. Resting atop the basilar membrane is the organ of Corti, which contains specialized sensory cells known as hair cells. These hair cells are the true transducers of the auditory system. Transduction is the process of converting one form of energy into another. As the basilar membrane vibrates, the hair cells bend. This bending opens tiny ion channels in their membranes, allowing electrically charged particles to flow into the cells. This movement of ions generates electrical signals. These signals are then transmitted along the auditory nerve, also called the cochlear nerve, to the brainstem. From there, The information travels through a series of neural pathways to the auditory cortex in the temporal lobe of the brain. It is in the auditory cortex that patterns of electrical activity are interpreted as speech, music, environmental sounds, or warning signals. The entire process, from vibrating air molecules to conscious perception, occurs in fractions of a second. Hearing ability, however, is not uniform across all individuals or across a lifetime. Age plays a significant role. As people grow older, the delicate hair cells in the cochlea can become damaged or die. Unlike many other cells in the body, these hair cells do not regenerate. High-frequency hair cells are often affected first, leading to gradual difficulty hearing higher-pitched sounds. This condition, known as presbycusis, is a common aspect of aging. Noise exposure can accelerate this process. Prolonged exposure to loud sounds can damage hair cells through mechanical stress and metabolic strain. Extremely loud noises can cause immediate and irreversible harm. The threshold at which damage becomes likely depends on both intensity and duration of exposure. The ear is resilient but not indestructible. Genetics also influence hearing. Some individuals are born with congenital hearing loss due to variations in genes responsible for hair cell development, cochlear structure, or neural transmission. Others may have inherited predispositions that affect hearing later in life. The ear must also maintain balance between sensitivity and protection. Small muscles in the middle ear can contract reflexively in response to loud sounds, reducing vibration transmission and providing limited protection. This acoustic reflex is not fast enough to prevent sudden damage from explosive noises, but it can moderate sustained loud input. What makes the human auditory system remarkable is its range and resolution. Under ideal conditions, it can detect vibrations at the threshold of hearing where pressure changes are incredibly small, and it can tolerate much larger amplitudes without immediate failure. It can distinguish subtle differences in pitch, timing, and spatial location, and yet it relies entirely on mechanical motion at its origin. Air vibrates, the eardrum moves, bones amplify, fluid shifts, membranes ripple, hair cells bend, ions flow, electrical impulses fire, the brain interprets. There is no break in the chain. The ear does not create sound. It receives patterns of pressure variation and translates them into neural language. Every word spoken, every melody played, every distant rustle is converted from mechanical energy into electrical signals through this elegant sequence. It is easy to forget how intricate this process is because it feels effortless. Sound arrives and meaning follows. But beneath that simplicity lies one of the most refined sensory systems in biology. A spiral of fluid and membrane, responding faithfully to the invisible rhythm of the world. It is natural to think of silence as the absence of sound. But in physics, silence is rarely absolute. Even in the quietest environments on Earth, air molecules continue to move. Thermal motion never fully stops. The question then becomes more precise. What is the quietest sound a human being can actually detect? The answer lies in something known as the threshold of hearing. The threshold of hearing is defined as the minimum sound pressure level that an average young, healthy human ear can detect under ideal laboratory conditions. This threshold depends on frequency, because the ear is not equally sensitive to all vibration rates. Around a frequency of roughly 1,000 cycles per second, human hearing is particularly sensitive. At that frequency, the smallest detectable sound corresponds to a pressure variation of about 20 micropascals. That number may not mean much at first glance, but it is extraordinarily small. Atmospheric pressure at sea level is about 100,000 pascals. A change of 20 micropascals is a tiny fraction of that baseline pressure, roughly 1 part in 5 billion, and yet the ear can detect it. To describe such enormous ranges of pressure in manageable numbers, scientists use a logarithmic scale known as the decibel scale. Sound pressure level is measured in decibels, which compare a given sound pressure to a reference value, typically the threshold of hearing. 0 decibels does not mean zero sound. it means the sound pressure equals the reference pressure of 20 micropascals. Because the decibel scale is logarithmic, an increase of 10 decibels represents a 10-fold increase in sound intensity. An increase of 20 decibels represents a 100-fold increase in intensity. This scaling reflects the way human perception works. The ear responds roughly logarithmically to changes in intensity, so the decibel scale aligns with perception more naturally than a linear scale would. Detecting extremely faint sounds presents significant challenges. At very low sound pressure levels, background noise becomes a limiting factor. Thermal noise in the air, vibrations from distant traffic, even the subtle hum of electrical systems can mask faint signals. In laboratory settings, researchers must isolate environments carefully to measure sounds near the threshold of hearing. One of the most famous environments designed for this purpose is the anechoic chamber. An anechoic chamber is a room constructed to eliminate reflections of sound. Its walls are covered with wedge-shaped acoustic foam that absorbs sound waves rather than reflecting them. The floor is often suspended on vibration isolators to reduce transmission of external noise. Some of the quietest anechoic chambers ever built have measured sound levels below 0 decibels. This does not mean they violate physics. It simply means the background sound pressure inside the chamber is lower than the standard threshold of hearing for an average person. Visitors to such rooms often report unusual experiences. In the absence of external sound, internal bodily noises become noticeable. The beating of the heart, the movement of blood through vessels, even faint ringing within the ears can emerge into awareness. Absolute silence, as it turns out, is not only rare but psychologically striking. The perception of extremely faint sound depends on more than just physics. It also depends on the sensitivity of the auditory system. Studies in psychoacoustics, the field that examines the relationship between physical sound and perception, have explored how attention, expectation, and neural processing influence what is heard. Researchers have found that the threshold of hearing is not fixed. It varies slightly among individuals and can fluctuate with fatigue, health, and environmental conditions. Noise-induced hearing loss, even at mild levels, can elevate the threshold, making faint sounds harder to detect. Prolonged exposure to loud environments can damage the hair cells within the cochlea, reducing sensitivity. This damage often begins at higher frequencies, but overall sensitivity can decline as well. Over time, the quietest detectable sound becomes louder in absolute terms because the auditory system has lost some of its responsiveness. There is also a physical limit imposed by the thermal motion of molecules in the air. Even in the absence of external sources, air molecules are constantly colliding due to temperature. This motion creates minute pressure fluctuations known as thermal noise. At some level, this sets a fundamental floor below which detecting sound becomes increasingly difficult. The study of human hearing sensitivity has been refined through decades of controlled experiments. Participants sit in sound-isolated booths wearing calibrated headphones. Pure tones at specific frequencies are presented at gradually decreasing intensities. The point at which the listener can no longer reliably detect the tone defines the threshold for that frequency. From these measurements, scientists construct equal loudness curves, which map how sensitivity varies across frequencies. These curves show that the ear is most sensitive to mid-range frequencies, particularly those important for speech. The idea of the quietest sound in the universe may sound poetic, but in practice, it is grounded in measurable limits. It is defined by the smallest pressure fluctuation the auditory system can convert into a meaningful neural signal. It is constrained by both physical and biological boundaries, and yet, even at those limits, the ear remains astonishingly capable. A pressure change so small it barely disturbs the atmosphere can still trigger a cascade of events inside the cochlea. Hair cells bend, ion channels open, electrical impulses travel along the auditory nerve, the brain registers presence. The faintest detectable sound is not dramatic. It does not announce itself with grandeur. It is subtle, almost fragile. but it represents the boundary between silence and sensation. In that boundary lies a reminder of how finely tuned the auditory system truly is. Even the gentlest ripple in the air can become part of conscious experience. And perhaps that is why quiet, when found, feels so rare. The world is constantly in motion. Molecules shift, structures vibrate, energy moves. To approach the threshold of hearing is to approach the delicate edge of perception itself. If the faintest sound rests at the edge of perception, the loudest sounds push at the edge of tolerance. Sound is, at its core, variation in pressure. When those pressure variations grow large enough, they do more than inform the ear. They begin to exert force, and force, when strong enough, can change matter itself. Sound pressure level is measured in decibels, a logarithmic unit that compares a given sound pressure to the standard reference level of 20 micropascals. Because the scale is logarithmic, increases in decibels represent rapid growth in intensity. An increase of 10 decibels corresponds to a tenfold increase in sound intensity. An increase of 20 decibels corresponds to a 100-fold increase. Normal conversation typically occurs around 60 decibels. Busy city traffic might reach 80 or 90 decibels. A rock concert or jet engine at close range can exceed 120 decibels. At that level, sound is no longer just heard, it is felt. The threshold of pain for many individuals lies around 130 decibels. At this intensity, pressure fluctuations are so strong that the sensation becomes physically uncomfortable. Beyond that, the risk of damage increases sharply. Inside the ear, the delicate hair cells of the cochlea are designed to respond to vibration, but they are not indestructible. Extremely loud sounds can bend these hair cells beyond their elastic limits. When that happens, the microscopic structures responsible for transducing sound into electrical signals may become permanently damaged. This condition is known as noise-induced hearing loss. It can result from a single intense event, such as an explosion, or from prolonged exposure to moderately high sound levels. The damage often begins with high-frequency hair cells, reducing sensitivity to higher pitches. Over time, speech perception may become more difficult, particularly in noisy environments. Temporary threshold shifts can also occur. After attending a loud event, hearing may feel muffled for several hours. This temporary change reflects metabolic stress within the cochlea. If exposure is repeated frequently, temporary changes can become permanent. Sound at extreme intensities can do more than damage hearing. It can affect the entire body. Very loud noise activates the sympathetic nervous system, increasing heart rate and stress hormone levels. Chronic exposure to high environmental noise has been associated with sleep disruption, elevated blood pressure, and increased risk of cardiovascular disease. The World Health Organization has conducted research on environmental noise and public health, identifying traffic noise and urban sound pollution as significant concerns in densely populated regions. Long-term exposure to elevated noise levels is not merely an annoyance. It can influence stress regulation, concentration, and overall well-being. The physical power of sound becomes even more dramatic when objects move at speeds approaching or exceeding the speed of sound in air. When an aircraft travels faster than sound, it outruns the pressure waves it generates. These waves accumulate and form a shock wave. When this shock wave reaches the ground, it is heard as a sonic boom. A sonic boom is not a single explosive event at the aircraft itself. It is the result of compressed airwaves merging into a sharp pressure front. The sudden change in pressure can rattle windows and, in extreme cases, cause structural damage. The Concorde supersonic aircraft produced such booms during flight, leading to restrictions on supersonic travel over populated land areas. At even higher intensities, sound waves can cause structural damage directly. Explosions generate rapid pressure spikes that can shatter glass, deform metal, and destabilize buildings. The destructive force arises from rapid and extreme pressure variation. In such cases, sound merges with shock physics and blast wave dynamics. In nature, loud sounds can also influence ecosystems. Marine animals are particularly sensitive to underwater noise. Industrial activities, shipping traffic, and naval sonar systems introduce high-intensity sounds into ocean environments. Some research suggests that intense sonar exposure may disrupt navigation in marine mammals, potentially contributing to strandings. Because sound travels efficiently in water, underwater noise can propagate across long distances. This has raised concerns about the cumulative impact of human-generated noise on marine communication and behaviour. Scientists continue to study how chronic exposure affects feeding, migration, and reproduction. Even on land, persistent environmental noise can alter animal behaviour. Birds may shift the pitch of their songs in urban areas to compete with low-frequency traffic noise. This adaptation reflects the interaction between acoustic physics and biological survival. Despite its potential for harm, loud sound also has beneficial applications. In medicine, high-intensity focused ultrasound can be used therapeutically to break apart kidney stones or target specific tissues without invasive surgery. In industrial settings, controlled shock waves can test material strength. The same physical principle that shatters glass can, when carefully harnessed, solve medical and engineering challenges. The relationship between amplitude and perceived loudness is not perfectly linear. Doubling the amplitude of a sound wave does not simply double its perceived loudness. Human hearing interprets intensity changes logarithmically, which is why the decibel scale aligns well with perception. It is important to distinguish between sound pressure level and subjective loudness. Two sounds with the same decibel rating may be experienced differently depending on frequency. The ear is more sensitive to mid-range frequencies than to very low or very high frequencies. As a result, a low-frequency rumble at a given decibel level may feel less intense than a mid-frequency tone at the same level. The power of loud sound lies not only in its intensity, but in its ability to influence matter and biology. Pressure waves can move objects, stress tissues, and alter behaviour. They can energize a crowd at a concert or disrupt sleep in a city apartment, and yet the mechanism remains consistent with the simplest whisper. It is still air being compressed and rarefied. The difference lies in magnitude. As amplitude increases, the energy carried by the wave grows rapidly. The physical force exerted by each compression becomes stronger. When that force exceeds biological tolerance or structural resilience, consequences follow. Sound, then, occupies a remarkable range. At its quietest, it barely disturbs the air. At its loudest, it reshapes environments and bodies alike. Between those extremes lies the delicate balance of hearing, where vibration becomes experience and where the power of pressure is translated into perception. If frequency determines how fast something vibrates, resonance determines how strongly it responds. Resonance occurs when an object is driven by a force at a frequency that matches its natural frequency. Every physical object, whether it is a violin string, a wine glass, or a suspension bridge, has one or more natural frequencies. These are the specific rates at which the object prefers to vibrate when disturbed. Natural frequency depends on physical properties such as mass, stiffness, and shape. A small, tight string vibrates naturally at a higher frequency than a long, loose one. A thick steel beam has a different natural frequency than a thin wooden plank. These frequencies are not chosen. They emerge from the balance between inertia and restoring force. When an external vibration matches that natural frequency, something remarkable happens. The energy transferred into the system accumulates efficiently. Each push arrives in rhythm with the object's motion, adding to its amplitude rather than disrupting it. The result is a dramatic increase in vibration. That amplification is resonance. It can be expressed simply as resonance occurs when driving frequency equals natural frequency. When spoken aloud, the principle sounds almost too neat, yet it governs everything from music to engineering. Musical instruments rely on resonance to produce rich sound. When a guitar string vibrates, it does not act alone. The body of the guitar resonates in response to the string's frequency. The wooden chamber amplifies specific frequencies and shapes the tone. Without resonance, the string's vibration would be faint and quickly damped. With resonance, it becomes full and sustained. Wind instruments operate on similar principles. A column of air inside a flute or organ pipe resonates at specific frequencies determined by its length and boundary conditions. Only certain frequencies fit neatly into the column as standing waves. These resonant frequencies become the musical notes the instrument produces. The concept of a standing wave is important here. When a wave reflects back and forth within a bounded space, certain frequencies create stable patterns of vibration with fixed nodes and antinodes. At these resonant frequencies, the wave reinforces itself. The energy does not dissipate randomly. It organizes into a coherent structure. Resonance, however, is not limited to music. In 1940, the Tacoma Narrows Bridge in the state of Washington collapsed dramatically. The bridge had exhibited visible oscillations in moderate wind conditions before its failure. On the day of its collapse, sustained winds interacted with the bridge structure in a way that excited one of its natural vibration modes. The oscillations grew in amplitude until the structure could no longer withstand the stress. Although the collapse involved complex aerodynamic effects known as aeroelastic flutter, rather than simple resonance alone, the underlying lesson was clear. Structures possess natural frequencies. When environmental forces match those frequencies, oscillations can grow dangerously large. Engineers now design buildings, bridges, and towers with careful attention to resonance. Skyscrapers include tuned mass dampers, which are heavy weights installed near the top of a structure. These dampers move out of phase with building vibrations, reducing resonant motion during wind or seismic activity. The goal is not to eliminate vibration entirely, but to prevent excessive amplification. Resonance can also shatter fragile objects. A glass has its own natural frequency. If exposed to a sound wave at that precise frequency and sufficient amplitude, the glass can vibrate intensely enough to fracture. While this requires both precision and high intensity, the principle remains grounded in the same physics that governs a violin. Beyond mechanical systems, resonance appears in electrical and electromagnetic systems as well. In the 19th century, Joseph Henry studied electromagnetic induction and resonance phenomena in electrical circuits. He demonstrated that circuits containing inductance and capacitance could exhibit resonant behavior where electrical oscillations grow large at specific frequencies. This form of resonance is foundational to radio communication. Tuning a radio involves adjusting a circuit so that it resonates at the frequency of a desired broadcast signal. When the circuit's natural electrical frequency matches the incoming signal, the amplitude of the electrical oscillation increases, allowing the signal to be detected clearly. Speakers and microphones also depend on resonant behavior. A loudspeaker contains a diaphragm attached to a voice coil. When an electrical signal passes through the coil, it creates a magnetic force that moves the diaphragm. The diaphragm and its enclosure are designed to resonate in controlled ways, enhancing certain frequency ranges while minimizing distortion. Medical devices use resonance as well. Magnetic resonance imaging, commonly known as MRI, relies on nuclear magnetic resonance. In this technique, atomic nuclei resonate at specific frequencies when placed in a strong magnetic field and exposed to radio frequency pulses. The resonant response provides detailed information about tissue structure. Though this is not acoustic resonance, the underlying principle of frequency matching remains the same. Resonance frequency is therefore the specific frequency at which a system naturally oscillates with maximum amplitude. It can be beneficial when harnessed deliberately. It can be destructive when excited unintentionally. What determines the sharpness of resonance is a property known as the quality factor, often abbreviated as Q factor. A system with a high quality factor resonates strongly at a narrow range of frequencies and sustains oscillations for longer periods. A system with a low quality factor has broader resonance and more rapid damping. In everyday language, a crystal wine glass has a higher quality factor than a thick rubber object. Damping is the process by which energy is lost from a vibrating system, usually through friction or resistance. Damping limits the amplitude of resonance. Without damping, even small periodic forces could lead to runaway oscillations. In practical systems, some damping is always present, providing stability. Resonance illustrates how energy transfer depends not only on force, but on timing. A child on a swing gains height when pushed at just the right moment in each cycle. Push at the wrong moment, and the swing slows down. The amplitude grows when force and motion align. In the natural world, resonance shapes behavior quietly. Vocal tracts resonate to produce distinct speech sounds. Cavities within the skull modify tone. Even the Earth has resonant frequencies, known as Schumann resonances, caused by electromagnetic waves trapped between the surface and the ionosphere. The phenomenon does not require intention. It emerges automatically whenever oscillatory systems interact. There is a certain elegance in this principle. Systems respond most strongly when stimulated at the rate they prefer. The match between driving frequency and natural frequency determines the outcome. Resonance can create music, transmit radio signals, produce medical images, or destabilize structures. It amplifies energy without adding new energy, simply by aligning timing and motion. And once recognized, it becomes clear that the world is filled with objects quietly tuned to particular rhythms, waiting to respond when the frequency is just right. Long before laboratories measured frequency and amplitude, the natural world was already fluent in sound. Across forests, oceans, deserts, and skies, animals use vibration as a tool for survival. Sound becomes language, radar, warning system, and invitation all at once. In many ecosystems, what is heard carries as much meaning as what is seen. Communication is perhaps the most familiar use of sound in nature. Birds sing to establish territory and attract mates. Each species produces calls shaped by its anatomy and environment. A songbird's syrinx, located at the base of its trachea, allows complex control of airflow and vibration. The result can be rapid shifts in pitch, layered harmonics, and intricate sequences of notes. These vocalizations are not random. They carry information about species identity, individual fitness, and territorial boundaries. In dense forests where visibility is limited, sound travels around obstacles, making it an efficient medium for signaling presence. In open savannas, elephants produce deep, resonant calls that can travel several kilometers. Some of these calls extend into the infrasonic range, below 20 cycles per second. Infrasound has long wavelengths, which bend around terrain and propagate efficiently through air and even ground. Herd members can detect these low-frequency signals through both hearing and subtle vibrations sensed through their feet. The use of infrasonic communication illustrates how animals exploit parts of the acoustic spectrum that humans rarely notice. For elephants, low-frequency sound is not mysterious, it is practical. At the other end of the spectrum lies ultrasound. Bats emit high-frequency pulses, often well above 20,000 cycles per second. These ultrasonic signals reflect off nearby objects and return as echoes. By analysing the timing and frequency shifts of these echoes, bats construct a detailed map of their surroundings. This process is known as echolocation. The American biologist Donald Griffin was among the first to demonstrate conclusively that bats use echolocation for navigation and hunting. In the 1940s, Griffin conducted experiments showing that bats could avoid obstacles in complete darkness, but struggled when their ability to emit or detect ultrasonic sounds was disrupted. His work revealed that sound could serve as a sensory system comparable to vision. Echolocation depends on precise timing. When a bat emits a pulse, it measures the delay before the echo returns. Because the speed of sound in air is known, the time delay reveals the distance to the object. Short delays indicate nearby prey. Longer delays signal distant obstacles. Dolphins and some species of whales also use echolocation, though underwater. In water, sound travels faster and farther than in air. Dolphins produce focused ultrasonic clicks and receive echoes through specialized structures in their lower jaws. These echoes are transmitted to the inner ear, where they are interpreted with remarkable accuracy. For a dolphin, the ocean is not silent darkness. It is an acoustic landscape filled with returning signals. Schools of fish, underwater terrain, and even small objects can be detected through reflected sound waves. Whales, particularly baleen whales, use sound differently. Many produce powerful low-frequency calls that travel across ocean basins. These vocalizations can serve as long-distance communication between individuals separated by hundreds or even thousands of kilometers. Because low-frequency waves attenuate less rapidly in seawater, they maintain coherence over vast distances. Birds also rely on sound not only for communication but for coordination. Certain species adjust the pitch of their songs in urban environments to compete with low-frequency traffic noise. This shift reflects an adaptive response to changes in acoustic background. Sound in nature is shaped by physics. Forests absorb high-frequency sounds more readily than low-frequency ones due to scattering and reflection by leaves and branches. Open plains allow calls to travel further. Underwater environments transmit low-frequency waves efficiently, but may distort higher frequencies over long distances. Predators and prey alike have evolved, hearing ranges suited to their ecological niches. Owls possess asymmetrical ear openings that allow precise localization of prey in darkness. Frogs call at frequencies that carry well across wetlands. Even insects use vibration transmitted through plant stems as a communication channel. The survival advantage of acoustic signaling lies in its speed and reach. Light requires a clear line of sight. Chemical signals can be slow to disperse. Sound moves quickly and can travel around obstacles. It allows immediate exchange of information. There is also subtlety in these systems. Many animals combine frequency modulation, amplitude variation, and temporal patterns to encode complex messages. A bird's song may vary slightly depending on context. A dolphin's click pattern can change when targeting different prey. The natural world demonstrates that sound is not merely noise. It is structured vibration used with precision. Evolution has shaped anatomical structures to generate and detect specific frequency ranges. The syrinx of birds, the larynx of mammals, the specialized fatty tissues in dolphin heads all represent biological solutions to acoustic challenges. Even plants may respond to vibration. Some studies suggest that certain species alter growth patterns in response to specific frequencies, though research in this area continues to develop. From infrasonic rumbles beneath elephant herds to ultrasonic pulses guiding bats through the night, the acoustic spectrum is alive with activity beyond human perception. What seems silent to human ears may be filled with signals meaningful to other species. Donald Griffin's early work on echolocation opened the door to understanding that sound can function as a primary sense. It reshaped how biologists think about animal awareness and navigation. Nature does not waste energy. If a vibration can carry useful information, it becomes part of survival. And in forests at dusk, across open oceans and beneath darkened skies, the world hums with communication, shaped by physics and refined by evolution, long before humans began to measure it. Human hearing occupies only a narrow band of the acoustic spectrum. Below roughly 20 cycles per second lies infrasound. Above roughly 20,000 cycles per second lies ultrasound. These vibrations are no less real than the tones of speech or music. They simply fall beyond the limits of typical human perception. Infrasound consists of very low frequency waves with long wavelengths. At 10 cycles per second, for example, the wavelength in air stretches across many meters. These waves roll slowly through the atmosphere, often travelling long distances with relatively little loss of energy. Because of their length, they bend around obstacles easily and can propagate across landscapes and oceans. Natural processes generate infrasound regularly. Volcanic eruptions produce powerful low-frequency pressure waves. Thunderstorms generate infrasonic pulses as lightning heats and rapidly expands air. Earthquakes and landslides send low-frequency vibrations through both ground and atmosphere. Scientists have learned to monitor infrasound as a tool for understanding these events. Networks of sensitive microbarometers detect minute pressure fluctuations in the atmosphere. Because infrasound travels far and can bypass terrain features, it allows detection of distant explosions or volcanic activity. International monitoring systems established to verify nuclear test ban treaties rely in part on infrasound detection. There is ongoing research into whether subtle infrasonic changes may precede major earthquakes. Some studies suggest that ground deformation and gas release before seismic events may generate low-frequency atmospheric signals. While earthquake prediction remains scientifically challenging, monitoring infrasound provides valuable data about geophysical processes. Animals may sense infrasound in ways humans cannot. Elephants produce and detect low-frequency calls that extend into the infrasonic range. Their large ear structures and specialized inner ear sensitivity allow them to respond to distant rumbles. Some evidence suggests that certain animals become restless before earthquakes, possibly responding to low-frequency ground vibrations. The exact mechanisms remain under investigation, but the physics make such detection plausible. Because infrasonic waves have long wavelengths, they interact with large structures and landscapes differently than higher frequencies. They are less easily absorbed by vegetation and terrain. This makes them effective carriers of information across wide areas. Ultrasound, at the opposite end of the spectrum, involves extremely rapid vibrations. At 100,000 cycles per second, air molecules oscillate back and forth 100,000 times each second. The wavelengths become very short, often measured in millimeters when travelling through tissue or water. Short wavelengths allow ultrasound to resolve fine details. This property makes it invaluable in imaging. In the 1940s, Austrian neurologist Karl Dussek experimented with using ultrasonic waves to examine brain tissue. Although early attempts were limited by technology, his work helped establish the foundation for diagnostic ultrasound. Modern medical ultrasound systems transmit high-frequency sound pulses into the body. When these waves encounter boundaries between tissues with different acoustic impedance, part of the energy reflects back. The system measures the time delay between emission and echo. Because the speed of sound in soft tissue is approximately 1,500 meters per second, the time delay reveals the depth of the reflecting structure. By scanning across an area and processing many returning echoes, the system constructs an image. This method, known as pulse echo imaging, allows visualization of organs, blood vessels, and developing fetuses without ionizing radiation. The process relies entirely on reflection, impedance differences, and precise timing. Ultrasound is also used therapeutically. High-intensity focused ultrasound can concentrate acoustic energy at a specific point within the body. At sufficient intensity, the energy raises temperature locally or disrupts targeted tissue. This technique can treat certain tumours or break apart kidney stones in a procedure called lithotripsy. In industrial settings, ultrasonic testing examines the integrity of metal components. High-frequency waves are sent into materials, and reflections from cracks or voids reveal hidden flaws. The same principles that guide dolphins through murky waters help engineers detect microscopic defects. Biological effects of ultrasound depend on intensity and duration. At diagnostic levels, ultrasound is considered safe when used appropriately. At higher intensities, it can cause heating or mechanical stress. Careful regulation ensures that medical applications remain within safe limits. Infrasound also has biological effects. At high intensities, very low frequency vibrations can produce sensations of pressure or discomfort. Research has examined whether prolonged exposure to certain infrasonic environments influences mood or physiological responses. Results vary, and much depends on amplitude. At natural environmental levels, infrasound is typically harmless. The perception of these frequencies, even when not consciously heard, can sometimes occur indirectly. Vibrations may be felt through the body or detected by specialized sensory structures in animals. Human hearing remains tuned primarily to the range most relevant for speech and environmental awareness. The contrast between infrasound and ultrasound illustrates how frequency shapes interaction with matter. Long wavelengths travel far and wrap around obstacles. Short wavelengths resolve fine detail but attenuate more quickly in air. Each frequency band has distinct advantages. Physics provides the framework. Biological systems and technologies exploit it. Carl Dussek's early imaging experiments demonstrated that high-frequency sound could probe internal structures. Later refinements in electronics and signal processing transformed ultrasound into a routine clinical tool. Meanwhile, global infrasound monitoring networks listen for signals that reveal hidden geophysical events. What lies beyond human hearing is not empty. It is filled with structured vibration carrying information across scales. Beneath the threshold of hearing, slow waves roll quietly through air and earth. Above the upper limit, rapid oscillations reveal the inner architecture of living tissue. The acoustic spectrum extends far beyond everyday experience, yet its extremes remain governed by the same principles of frequency, wavelength, and propagation. Sound does not end where hearing ends. It continues outward in both directions, shaping environments, guiding animals, and revealing structures invisible to the eye. And in that broader spectrum, the strange world of infrasound and ultrasound becomes less mysterious and more like an extension of the same quiet laws that govern every vibration in the air around you. Sound does more than carry information about the world outside. It reaches inward. A sudden crash can trigger a surge of adrenaline before conscious thought even forms. A familiar melody can stir memory with surprising intensity. A steady rhythm can calm breathing without any deliberate effort. The pathway from vibration in the air to emotion in the mind is direct and deeply rooted in biology. When sound waves enter the ear and are converted into electrical signals, those signals do not travel only to the auditory cortex. They also interact with regions of the brain involved in emotion, memory, and physiological regulation. Structures within the limbic system, including the amygdala and hippocampus, respond to auditory input. This connection explains why certain sounds feel comforting, alarming, nostalgic, or unsettling. Music offers one of the clearest examples of sound influencing emotion. Changes in tempo, harmony, and pitch can alter mood rapidly. Slow tempos with gentle dynamics often encourage relaxation. Faster rhythms and higher intensities can stimulate alertness or excitement. Minor tonal structures may evoke melancholy, while major tonal structures are often associated with uplift. These emotional associations are shaped partly by culture and partly by biology. Certain acoustic features, such as sudden loud noises or sharp frequency shifts, activate neural circuits linked to threat detection. This response has evolutionary roots. Detecting danger quickly increased survival. A snapping twig in a quiet forest once carried urgent meaning. Nature sounds often produce different effects. The steady sound of rainfall, ocean waves, or wind moving through leaves tends to contain broad frequency distributions without abrupt changes. These soundscapes can promote relaxation by reducing perceived unpredictability. Some research suggests that natural acoustic environments support parasympathetic nervous system activity, which is associated with rest and recovery. White noise functions differently. White noise contains a broad spectrum of frequencies distributed evenly across the audible range. Because it lacks distinct patterns, it can mask sudden environmental sounds. This masking effect reduces interruptions and may improve sleep in noisy environments. The brain adapts to the steady acoustic background and becomes less reactive to random disturbances. Sound can influence measurable physiological markers. Studies have shown that calming music can reduce heart rate, lower blood pressure, and decrease levels of cortisol, a stress hormone. In hospital settings, patients exposed to relaxing music before surgery often report lower anxiety levels compared to those in silence. The field of music therapy uses structured musical interaction to support emotional and cognitive health. Certified music therapists work with individuals experiencing conditions such as depression, dementia, or neurological injury. Through rhythm, melody, and active participation, music can stimulate memory recall, improve mood, and enhance communication. In patients with Alzheimer's disease, familiar songs sometimes unlock memories that spoken prompts cannot reach. This effect highlights the strong connection between auditory processing and memory networks. Music appears to engage multiple brain regions simultaneously, creating durable associations. Sound therapy extends beyond music. Certain practices use sustained tones, singing bowls, or rhythmic patterns to encourage relaxation. While the scientific evidence varies depending on the method, the underlying mechanism often involves guiding breathing patterns and promoting attentional focus. One phenomenon frequently discussed in relaxation contexts is binaural beats. Binaural beats occur when two slightly different frequencies are presented separately to each ear. For example, if one ear receives a tone of 400 cycles per second and the other receives 410 cycles per second, the brain perceives a third rhythmic pulsing at 10 cycles per second. This perceived beat arises from neural processing rather than from physical interference in the air. Some researchers have explored whether binaural beats can influence brainwave patterns associated with relaxation or concentration. Brainwaves are patterns of electrical activity measured by electroencephalography. Certain frequency ranges, such as those between 8 and 12 cycles per second, are associated with relaxed wakefulness. While studies show mixed results, some evidence suggests that binaural stimulation may modestly influence subjective relaxation in certain individuals. The emotional impact of sound is also shaped by personal experience. A song linked to a significant life event may carry emotional weight unrelated to its acoustic structure. The brain stores auditory memories alongside contextual details, creating layered associations. Not all sound effects are beneficial. Chronic exposure to unwanted noise can elevate stress levels and impair concentration. Persistent environmental noise has been linked to sleep disruption and reduced cognitive performance in children. The unpredictability and lack of control over certain noise sources can amplify emotional strain. Silence, when chosen rather than imposed, can also influence emotional state. Periods of reduced auditory input may allow neural systems to recalibrate. Some studies suggest that quiet environments support memory consolidation and emotional processing. The relationship between sound and emotion is therefore multifaceted. It involves physical properties such as frequency and amplitude, neural circuitry connecting auditory pathways to emotional centers, and personal history shaping interpretation. Even subtle shifts in tone can change perception. A gentle voice can reassure. A harsh tone can provoke tension. The content of speech matters, but so does its acoustic character. Sound's influence on emotion underscores that hearing is not a detached sensory act. It is woven into the regulation of mood, attention, and social connection. Rhythms synchronize groups during music or collective activity. Lullabies calm infants through predictable melodic patterns and gentle tempo. In everyday life, the acoustic environment continuously shapes internal states. The hum of appliances, the murmur of conversation, the distant rush of traffic all contribute to a background that can either soothe or strain. The science behind these effects rests on measurable neural and physiological responses. Electrical signals from the ear interact with networks governing stress, memory, and reward. Neurotransmitters such as dopamine can be released during pleasurable musical experiences, reinforcing emotional engagement. Sound is vibration, but it is also experience. It can comfort, alert, inspire, or unsettle. It can quiet the mind or quicken the pulse. Through pathways refined by evolution and shaped by culture, pressure waves become feeling. And in that transformation from oscillation to emotion, the invisible motion of air finds its place within the human story. Silence seems simple. It is often described as the absence of sound, a pause between notes, a gap in conversation, a stillness in the air. Yet from a physical perspective, true silence is almost impossible. Air molecules continue to move due to thermal energy. The body generates internal vibrations. Even in the quietest environments, pressure fluctuations never reach absolute zero. What most people call silence is not the absence of vibration, but the absence of noticeable or meaningful sound. In daily life, silence can feel peaceful. A quiet forest at dawn, a snowfall absorbing distant noise, a room free from conversation or machinery. In these moments, the auditory system is no longer processing constant competing signals. The brain experiences reduced sensory load. This reduction can lower stress responses and allow attention to shift inward. Psychologists have examined how quiet environments influence mental states. Some studies suggest that periods of reduced auditory input can support memory consolidation and cognitive restoration. The brain's default mode network, active during rest and reflection, may become more engaged when external stimulation decreases. In natural environments, silence often reflects distance from human-generated noise. Yet even wilderness silence contains subtle sounds. Leaves rustle, insects hum faintly, distant birds call intermittently. These low-intensity soundscapes differ from urban silence, which may still carry background electrical hums or distant traffic rumble. The perception of silence depends partly on contrast. After prolonged exposure to loud environments, even moderate noise levels can feel quiet. After extended quiet, minor sounds can seem startlingly prominent. The auditory system adapts dynamically to context. Engineers who design recording studios and sound laboratories understand this adaptation well. They construct spaces known as anechoic chambers to minimize sound reflections and external noise. An anechoic chamber is lined with sound-absorbing wedges that prevent echoes. The floor is often suspended to reduce vibration from surrounding structures. Some of the quietest anechoic chambers ever built measure sound pressure levels below 0 decibels. This does not mean they contain negative sound. It means the measured pressure fluctuations are lower than the standard reference threshold of hearing. In such spaces, external noise is almost completely removed. People who spend time in these rooms often report unusual sensations. Without external sound cues, internal bodily sounds become noticeable. The heartbeat, the movement of joints, the faint ringing sometimes present in the ears all rise into awareness. Absolute silence, rather than feeling purely peaceful, can become unsettling. The reason lies partly in how the brain interprets sensory input. The auditory system evolved to detect environmental changes. In the absence of external signals, the brain may amplify internal noise to maintain sensitivity. This phenomenon can contribute to tinnitus, a perception of ringing or buzzing without external stimulus. Sound engineers and psychologists have studied how prolonged silence influences mood and perception. Short periods of quiet can reduce stress and improve concentration. Extended sensory deprivation, however, may alter time perception and heighten awareness of internal sensations. The psychological impact of silence varies with context. Chosen quiet, such as meditation or retreat, often promotes calm. Imposed silence, such as isolation without stimulation, can provoke discomfort. The difference lies in expectation and perceived control. In social settings, silence carries meaning beyond physics. A pause in conversation may signal reflection, tension, agreement, or uncertainty. Cultural norms shape how silence is interpreted. In some traditions, silence reflects respect and attentiveness. In others, Prolonged quiet may feel awkward. From a neurological perspective, silence allows auditory neurons to reduce firing rates associated with external stimuli. This can conserve energy and reset sensitivity. Research on neural plasticity suggests that alternating periods of stimulation and rest support healthy sensory processing. Even in music, silence plays an essential role. Composers use rest to create anticipation and contrast. The pause between phrases shapes emotional impact. Without silence, continuous sound would lose structure and clarity. In the natural world, quiet periods may signal safety or danger. A sudden hush in a forest can indicate the presence of a predator. The absence of expected background noise may draw attention precisely because it violates pattern. There is also a physical dimension to silence in space. In the vacuum beyond Earth's atmosphere, sound cannot propagate without a medium. The absence of air means mechanical waves do not travel. Yet spacecraft themselves are not silent. Vibrations within cabins, airflow systems, and machinery produce sound internally. Silence in space is therefore environmental rather than absolute. When humans seek silence, they often seek relief from unpredictability. Steady, low-intensity sound may feel calmer than abrupt noise. Complete absence of sound removes environmental cues, which can feel either liberating or disorienting. The boundary between sound and silence is defined by perception. The threshold of hearing marks one limit, but psychological interpretation defines experience. A faint whisper at night may feel loud, in contrast to stillness. The same whisper in a busy room might disappear unnoticed. Silence invites attention inward. It creates space for thought, memory, and subtle sensation. It can support recovery from sensory overload. It can also reveal that the body itself is never fully quiet. In laboratories designed to eliminate external vibration, researchers observe that most people can tolerate complete acoustic isolation only for limited periods. The mind begins to generate its own focus in the absence of incoming signals. Silence, then, is not empty. It is a condition of reduced external vibration, shaped by context and expectation. It is defined as much by the brain as by the air. Between the faintest detectable sound and the loudest roar lies a continuum. Silence occupies one end of perception, but never entirely escapes physics. Molecules continue to move, hearts continue to beat, and within that quiet space, awareness becomes sharper, revealing that even in stillness, the world is never completely at rest. Space is often described as silent, not quiet in the way a forest is quiet, not hushed like a snow-covered field, but fundamentally silent because the medium required for sound simply is not there. Sound is a mechanical wave. It depends on particles pushing and pulling on one another. In the vacuum of space, particles are so sparse that sustained compression and rarefaction cannot propagate in the familiar way. Between planets and stars, matter exists, but at densities so low that collisions between particles are rare. Without a continuous medium, pressure waves cannot travel. If two astronauts floated outside a spacecraft and one struck a metal panel with a tool, the other would not hear the impact through the vacuum between them. The vibration would remain confined to the structure that was struck. Yet space is not devoid of vibration. Inside a spacecraft or space station, there is air. That air supports sound in exactly the same way it does on Earth. Astronauts aboard the International Space Station hear fans circulating air, the hum of life support systems, the clicks of instruments, and the voices of crew members. NASA carefully monitors onboard sound levels because persistent noise can affect sleep, communication, and stress. In microgravity environments, sound propagation within the cabin follows the same physical principles as on Earth. Frequency, amplitude, and wavelength remain governed by the properties of the air and structural materials. However, the acoustic environment differs due to confined spaces and continuous mechanical systems. NASA has conducted studies to measure noise exposure in spacecraft habitats. Maintaining safe sound pressure levels is important for long-duration missions. Prolonged exposure to elevated noise can contribute to hearing fatigue or reduced communication clarity. Engineers design insulation and vibration damping systems to manage these risks. Outside the spacecraft, communication depends on electromagnetic waves rather than mechanical waves. Astronauts use radio communication systems that convert sound into electrical signals, which are then encoded onto radio frequency carriers. These radio waves are electromagnetic in nature. Unlike sound, they do not require a material medium and can travel through the vacuum of space at the speed of light. The process begins with a microphone converting air pressure variations into electrical signals. These signals modulate a radio frequency carrier wave. The modulated signal travels across space and is received by another radio antenna. The receiver demodulates the signal, reconstructing the original audio waveform. That waveform drives a speaker, which recreates the sound as mechanical vibration in air. In this way, sound becomes information carried by electromagnetic radiation and then reassembled at its destination. Training for space missions often includes simulation of acoustic environments. Astronauts practice communication protocols in mock spacecraft cabins. Engineers analyze how reverberation and background noise affect speech intelligibility. Clear communication is essential when operating complex systems in challenging conditions. Even though space itself does not transmit sound in the traditional sense, vibrations still exist in other forms. One example is plasma waves. In regions of space filled with ionized gas, such as the solar wind, particles can oscillate collectively. Spacecraft instruments detect fluctuations in electric and magnetic fields associated with these oscillations. Scientists sometimes convert these signals into audible frequencies for analysis. While the original waves are not sound waves traveling through air, their frequency patterns can be translated into the human auditory range. Gravitational waves provide another fascinating example. Predicted by Albert Einstein's general theory of relativity and first directly detected in 2016 by the Laser Interferometer Gravitational Wave Observatory, gravitational waves are ripples in space-time itself. They are produced by massive accelerating objects, such as merging black holes or neutron stars. Gravitational waves are not sound waves. They do not propagate through air or water. They represent oscillations in the fabric of space-time. However, when their frequency data are converted into audible sound, they produce characteristic chirps. The frequency increases rapidly as two massive objects spiral closer together before merging. The conversion into sound allows scientists and the public to hear patterns that would otherwise remain abstract. In this sense, sound becomes a bridge between human perception and cosmic events. The absence of a medium in interstellar space emphasizes how dependent sound is on matter. Without particles close enough to transfer pressure, mechanical waves cannot sustain themselves. This limitation highlights the difference between mechanical waves and electromagnetic waves. Inside planetary atmospheres, however, sound behaves normally. On Mars, for example, the atmosphere is much thinner than Earth's. Sound can travel, but its speed and attenuation differ due to lower density and temperature. Instruments aboard robotic missions have recorded wind and mechanical sounds, providing insight into acoustic behavior under Martian conditions. Even the Sun produces oscillations. The field of helioseismology studies pressure waves traveling within the Sun's interior. These waves arise from convective motion and can be detected through changes in solar surface brightness. Scientists analyze these oscillations to learn about the Sun's internal structure. Although the Sun's interior is plasma rather than air, pressure waves still exist within that medium. Space may be silent to unaided human ears, but it is not static. Vibrations occur wherever matter exists. Inside spacecraft, air carries familiar sound. Within stars, plasma supports oscillations. Across space-time, gravitational waves ripple outward from violent cosmic events. The phrase "silence of space" captures a specific physical truth. Without a continuous medium, mechanical sound cannot travel between distant objects. yet vibration remains fundamental to the universe. When astronauts speak in orbit, their voices move through cabin air, become radio signals, and cross the vacuum as electromagnetic waves. When detectors measure gravitational waves, their data can be rendered into audible form, transforming space-time ripples into recognizable tones. Sound then remains rooted in matter. It requires particles, pressure, and elasticity. Space reminds us of that dependence. Remove the medium, and the wave cannot propagate. But where matter gathers, even in orbit or within distant stars, vibration resumes its quiet work, carrying energy, shaping perception, and linking motion to meaning once again. Sound technology has never stood still. From the first phonograph cylinders to digital streaming, each generation has reshaped how vibration is captured, transmitted, and experienced. Yet the most interesting changes may still be unfolding as physics, neuroscience, and computing converge. One of the most visible developments is three-dimensional audio, often called spatial audio. Traditional stereo sound uses two channels, left and right, to create a sense of width. Three-dimensional systems aim to reproduce not only width, but height and depth. The goal is to simulate how sound behaves in the real world, where waves arrive at the ears from multiple directions with subtle timing differences. The science behind this relies on head-related transfer functions. These functions describe how the shape of the head, ears, and torso modify incoming sound waves. By modelling these modifications, engineers can create audio that appears to originate from specific points in space. When implemented effectively, the listener perceives sound above, behind, or moving around them. Companies such as Dolby Laboratories and Sony have developed spatial audio platforms that integrate these principles into cinema, music streaming, and gaming systems. In virtual reality environments, three-dimensional sound is not optional. It is essential. Without accurate spatial cues, immersion breaks. The brain expects audio to match visual motion and head orientation. Active noise cancellation represents another remarkable innovation. Instead of blocking sound with heavy materials alone, active systems generate sound waves designed to interfere destructively with unwanted noise. A microphone detects incoming sound, electronics calculate an inverted waveform. A speaker emits that inverted signal. When the two waves meet, they partially cancel. The principle is simple wave superposition. When two waves of equal amplitude and opposite phase combine, their pressure variations reduce. In practice, achieving effective cancellation requires rapid processing and precise timing. Companies such as Bose Corporation refined consumer active noise cancellation headphones over decades, combining acoustic engineering with digital signal processing. Soundproofing technology has also advanced. Modern architectural acoustics uses layered materials with different densities to manage acoustic impedance mismatches. Mass-loaded vinyl, specialized foam composites, and double-wall constructions reduce sound transmission. Research institutions studying metamaterials are exploring structures that manipulate sound waves in unconventional ways, bending or absorbing them more efficiently than traditional materials allow. Metamaterials are engineered structures designed to exhibit properties not typically found in natural materials. By arranging components in repeating patterns smaller than the wavelength of interest, researchers can create materials that block specific frequencies or guide sound along controlled paths. This area of acoustic metamaterials holds promise for future sound control systems in buildings and vehicles. In medicine, ultrasound technology continues to evolve. Portable ultrasound devices now connect tablets and smartphones, allowing imaging in remote locations. Researchers are exploring focused ultrasound not only for breaking kidney stones, but also for non-invasive brain stimulation. Low-intensity ultrasound pulses can influence neural activity, offering potential treatments for certain neurological conditions. Institutions such as the Massachusetts Institute of Technology and Stanford University conduct research into ultrasonic neural modulation, Although still under investigation, the concept relies on mechanical energy influencing ion channels and neural firing patterns. Sound-based therapies also continue to develop. Music therapy has gained recognition in clinical settings for supporting recovery from stroke and improving mood in patients with depression. Structured rhythmic stimulation can assist in motor rehabilitation by entraining movement patterns. The brain's ability to synchronize to rhythm, known as neural entrainment, provides a mechanism for these effects. Virtual reality systems increasingly integrate advanced audio modeling. Companies such as Meta and Valve invest in real-time spatial audio engines that simulate reverberation, occlusion, and environmental acoustics dynamically. When a virtual door closes, the sound changes realistically. When the user turns their head, the perceived source shifts accordingly. The technology depends on detailed acoustic modeling and rapid computational updates. Engineering applications of sound extend into industrial monitoring. Acoustic emission sensors detect stress fractures in bridges, aircraft, and pipelines by capturing high-frequency vibrations produced by microcracks. These systems act as early warning detectors, identifying structural issues before catastrophic failure occurs. Researchers are also exploring acoustic levitation. By using precisely tuned ultrasonic waves, small particles or droplets can be suspended in air. The standing wave pattern creates nodes where pressure forces counteract gravity. While currently used in laboratory demonstrations and material science experiments, such techniques may one day contribute to contact-free manufacturing processes. Scientific advancements are changing how humans interact with sound at every level. Machine learning algorithms now enhance speech recognition in noisy environments. Digital signal processing allows real-time modification of acoustic properties. Hearing aids incorporate adaptive filters that adjust automatically to changing soundscapes. Even architectural design increasingly integrates acoustic simulation during planning stages. Software models how sound will behave within a space before construction begins. This predictive capability allows concert halls to be optimized for clarity and warmth, without relying solely on post-construction adjustments. Entertainment systems are evolving toward immersive experiences that combine spatial audio with haptic feedback. Low-frequency transducers embedded in seating can convert sound energy into tactile vibration, allowing listeners to feel bass frequencies physically. The boundary between hearing and touch becomes blurred. As these technologies advance, ethical and health considerations follow. Extended headphone use at high sound pressure levels can contribute to hearing loss. Designers balance immersion with safety by limiting output and incorporating protective algorithms. The future of sound technology rests on deeper understanding of wave physics, perception, and digital processing. Innovations are guided by the same principles that govern a vibrating string or a passing siren. Frequency, amplitude, wavelength, and resonance remain foundational concepts. What changes is the precision with which those principles are applied. Three-dimensional audio refines spatial cues. Active noise cancellation manipulates phase relationships. Focused ultrasound directs energy with millimeter accuracy. Metamaterials reshape wave propagation itself. Sound, once limited to direct acoustic experience, now travels through digital networks, computational models, and engineered materials before reaching the ear. The interaction between vibration and technology grows more sophisticated each year. Yet beneath the layers of innovation, the essence remains unchanged. Sound is still organized motion in matter. It is still pressure variation shaped by physical laws. The difference lies in control. Humans are learning not only to hear sound, but to sculpt it deliberately, to cancel it, amplify it, redirect it, and translate it into forms that extend beyond hearing alone. The future will likely bring environments where sound adapts dynamically to context, where acoustic spaces are programmable, and where vibration serves purposes not yet fully imagined. And through all of it, the invisible rhythm of pressure waves will continue to shape experience, guided by science and refined by ingenuity. Every environment has a voice. A forest at dawn carries layered bird calls, rustling leaves, and distant insect rhythms. A coral reef hums with a crackle of snapping shrimp and the low murmurs of fish. A city vibrates with engines, footsteps, ventilation systems, and fragments of conversation. These combined acoustic signatures form what researchers call a soundscape. A soundscape is the total collection of sounds in a particular place. It includes biological sounds from animals, geophysical sounds such as wind or rain, and human-generated noise. The concept was developed and expanded by acoustic ecologists such as R. Murray Schafer in the 20th century, who argued that environments can be understood not only visually but acoustically. In natural ecosystems, sound plays an essential role in shaping behaviour and interaction. Many species rely on acoustic communication to establish territory, locate mates, warn of predators, or coordinate group movement. Because sound travels efficiently around obstacles and through vegetation, it becomes especially important in habitats where visibility is limited. In dense forests, bird species often occupy distinct frequency bands to avoid overlapping calls. This phenomenon, sometimes called acoustic niche partitioning, reduces interference and allows multiple species to communicate effectively within the same habitat. Each species, in a sense, finds its own frequency space. Underwater ecosystems rely even more heavily on sound. Light attenuates quickly in water, especially at depth. Sound, by contrast, travels far and fast. Marine mammals, fish, and invertebrates use acoustic signals to navigate, locate prey, and communicate across large distances. Coral reefs generate a characteristic acoustic signature that helps larval fish identify suitable habitats. Environmental researchers record underwater soundscapes to assess ecosystem health. A diverse and active reef tends to produce a complex acoustic pattern. Degraded reefs often become quieter. In this way, sound becomes an indicator of biological vitality. Human presence alters these soundscapes dramatically. Road traffic, aircraft, industrial machinery, and shipping introduce persistent noise into environments that once followed natural acoustic rhythms. This phenomenon is known as noise pollution. Unlike visible pollution, it leaves no residue on surfaces, yet its impact can be profound. Noise pollution affects wildlife in several ways. It can mask communication signals, making it harder for animals to detect mates or warnings. It can alter behaviour by causing stress or displacement. Chronic noise exposure may influence feeding patterns, migration routes, and reproductive success. Research conducted by environmental organisations such as the United States National Park Service and the European Environment Agency has examined how anthropogenic noise affects wildlife. Studies show that some bird species increase the pitch of their songs in urban environments to compete with low-frequency traffic noise. Others abandon habitats entirely when noise levels exceed certain thresholds. Marine environments face similar challenges. Commercial shipping produces low-frequency noise that travels efficiently through ocean water. Naval sonar systems generate high-intensity acoustic pulses. Research published in marine biology journals suggests that intense sonar exposure may disrupt the navigation of certain whale species. The precise mechanisms remain under investigation, but behavioural changes have been documented. Even moderate levels of chronic environmental noise can influence physiological stress responses in animals. Elevated stress hormones may reduce immune function or reproductive success over time. The impact is not always immediately visible, but it accumulates. For humans, environmental noise also carries health implications. Long-term exposure to traffic noise has been associated with sleep disturbance, reduced concentration, and increased risk of cardiovascular disease. The World Health Organization has identified environmental noise as a public health concern in densely populated regions. The acoustic environment shapes experience as much as architecture or climate. A quiet, natural setting often supports relaxation and cognitive recovery. Studies in environmental psychology suggest that exposure to natural soundscapes can lower stress and improve mood compared to exposure to mechanical noise. The concept of soundscape ecology has emerged as a scientific field integrating acoustics, biology, and environmental science. Researchers deploy autonomous recording units in forests, grasslands, and oceans to monitor changes over time. By analysing frequency distributions and temporal patterns, they assess biodiversity and detect shifts linked to climate change or habitat disturbance. Sound interacts with ecosystems not only as communication, but also as physical energy. Low-frequency vibrations from heavy machinery can travel through soil, potentially affecting burrowing animals. Construction noise may displace species during sensitive breeding periods. Urban planners increasingly recognise the importance of acoustic design. Incorporating green spaces, sound barriers, and traffic flow management can reduce noise levels and improve quality of life. The goal is not absolute silence, but balance. Even in seemingly quiet landscapes, subtle acoustic patterns define ecological identity. Desert environments carry the sound of wind shaped by terrain. Wetlands resonate with amphibian choruses at specific times of year. Seasonal cycles alter soundscapes as migration and breeding behaviours shift. Climate change may also influence environmental acoustics. Changes in vegetation density, temperature gradients, and ocean chemistry can modify how sound propagates. Warming ocean waters alter sound speed slightly, affecting long-distance marine communication. Melting sea ice changes the acoustic properties of polar regions. The environment, then, is not only seen and touched, it is heard. When human activity introduces continuous mechanical noise, it overlays natural rhythms with new frequencies and amplitudes. Some species adapt, others struggle. The acoustic niche shifts. Understanding sound as an ecological factor broadens awareness of environmental stewardship. Preserving habitats includes preserving their acoustic integrity. Protected natural areas often emphasize limiting motorized noise to maintain ecological function and visitor experience. The relationship between sound and environment is dynamic. Animals shape soundscapes through vocalization. Weather contributes through wind and water. Humans alter them through technology and infrastructure. Sound does not remain passive in these interactions. It carries information, influences behavior, and affects health across species. In every habitat, from rainforest canopy to ocean floor, vibration threads through daily life. The environment speaks continuously, and its voice reflects the balance between natural processes and human presence. Listening carefully reveals that ecosystems are not silent backdrops. They are acoustic communities shaped by physics and biology together, where every call, hum, and ripple plays a role in the larger harmony of place. Long before microphones and amplifiers, architecture was already shaping sound. In ancient Greece, open-air theatres were carved into hillsides with remarkable acoustic sensitivity. The Theatre of Epidaurus, constructed in the 4th century before the Common Era, is often cited as an example. Its semicircular seating arrangement and stepped limestone rows reflect and distribute sound efficiently. Even a quiet voice from the stage can carry clearly to distant seats. The geometry supports direct sound paths while minimizing disruptive echoes. These early builders did not possess digital modeling software, yet through observation and refinement they discovered principles that remain valid today. Shape, material, and proportion determine how sound behaves within a space. Sound inside a building reflects, absorbs, and diffuses depending on surfaces it encounters. Hard, smooth materials such as stone or glass reflect most acoustic energy. Soft, porous materials such as fabric and specialized foam absorb portions of it. The balance between reflection and absorption defines the character of a room. One of the most important concepts in architectural acoustics is reverberation time. Reverberation time refers to how long it takes for sound to decay after the source stops. In a cathedral, reverberation may last several seconds, producing a rich, lingering effect. In a classroom, excessive reverberation can reduce speech intelligibility. The optimal reverberation time depends on the intended use of the space. Concert halls are designed with particular care to achieve a balance between clarity and warmth. Too little reverberation and music feels dry. Too much and individual notes blur together. Architects and acoustic engineers work together to shape surfaces that scatter sound evenly, rather than focusing it unpredictably. Acoustic engineering is the discipline dedicated to controlling sound within built environments. It combines wave physics, material science, and perceptual research. Engineers calculate how sound waves will reflect from walls and ceilings. They consider the frequency-dependent absorption coefficients of materials. They simulate standing wave patterns that might amplify certain frequencies excessively. Modern concert halls often include adjustable acoustic elements. Movable panels, curtains, and reflectors allow the reverberation characteristics to be modified depending on whether the performance involves a symphony orchestra, a solo pianist, or spoken word. The design aims to support natural amplification without electronic reinforcement when possible. One famous example is the Berlin Philharmonie, completed in 1963. Its vineyard-style seating surrounds the stage, distributing sound energy more evenly throughout the hall. The irregular geometry reduces strong echoes and promotes balanced reflection. Beyond concert halls, acoustic design influences everyday spaces. Open-plan offices, while visually spacious, can suffer from excessive noise and reduce privacy. Architects address this by incorporating sound-absorbing ceiling tiles, carpeted floors, and partition panels. The goal is to reduce overall sound pressure levels and limit distracting reflections. Hospitals also benefit from careful acoustic planning. High noise levels in medical environments can interfere with communication and increase stress for patients and staff. Acoustic treatments in corridors and patient rooms help create calmer environments that support recovery. Urban architecture must also contend with external noise sources. Traffic, aircraft, and industrial activity generate continuous sound. Building facades incorporate double glazing, laminated glass, and insulated wall assemblies to reduce sound transmission. The effectiveness of these measures depends on acoustic impedance and mass law principles. Heavier, denser materials tend to block sound more effectively, particularly at lower frequencies. The relationship between structure and vibration extends beyond airborne sound. Buildings themselves can vibrate due to mechanical systems or external forces. Acoustic engineers analyze structural resonance to prevent amplification of unwanted noise. Mechanical equipment is mounted on vibration isolators to prevent transmission through floors and walls. Sound designers contribute as well. In theatres and public venues, electronic sound reinforcement systems must integrate with architectural acoustics. Speakers are positioned to provide even coverage while minimizing feedback. Delay systems ensure that amplified sound reaches distant seats in synchrony with direct sound from the stage. The history of acoustic design reflects increasing scientific understanding. In the late 19th century, physicist Wallace Clement Sabine conducted systematic studies of reverberation in lecture halls at Harvard University. Sabine established quantitative relationships between room volume, surface absorption, and reverberation time. His work laid the foundation for modern architectural acoustics. Sabine demonstrated that reverberation time could be estimated based on the total absorption within a room. This insight allowed architects to predict acoustic behavior before construction. The integration of measurement and theory transformed acoustic design from intuition to science. Today, computer modeling software simulates how sound will travel within proposed structures. Ray tracing algorithms calculate reflection paths. Finite element analysis models vibration patterns. These tools allow refinement before physical materials are assembled. Architectural acoustics also considers psychoacoustics. The subjective experience of sound quality depends on more than decibel levels. Early reflections arriving within specific time windows enhance clarity and spatial impression. Excessive late reflections reduce intelligibility. Engineers balance these factors to create comfortable listening environments. Even small design choices matter. Curved surfaces can focus sound if not carefully shaped. Flat parallel walls may create flutter echoes. Textured surfaces scatter sound, reducing harsh reflections. Ceiling height influences reverberation and perceived spaciousness. In residential settings, acoustic comfort contributes to well-being. Proper insulation reduces intrusion from neighbouring units. Interior materials influence how voices and music are experienced within rooms. A comfortable acoustic environment supports conversation and rest. Architecture, therefore, becomes an instrument. Its walls and ceilings shape vibration just as the body of a violin shapes string resonance. Sound interacts continuously with structure. The built environment is never acoustically neutral. It either enhances clarity or introduces confusion. It either absorbs excess energy or reflects it unpredictably. Thoughtful design transforms potential noise into controlled experience. From ancient amphitheatres carved into stone to modern concert halls modelled with digital precision, the partnership between sound and architecture has evolved steadily. Acoustic engineers, architects, and sound designers collaborate to ensure that vibration serves its purpose rather than overwhelming it. The result is not merely silence or amplification, it is balance. Within well-designed spaces, voices carry clearly, music resonates richly, and unwanted noise recedes into the background. The invisible motion of air finds harmony with the structures that contain it, and in that harmony, architecture reveals itself not only as shelter, but as a careful sculptor of sound. The future of sound may not simply be louder or clearer, it may be more immersive, more responsive, and more deeply integrated into how reality itself is experienced. Virtual and augmented reality systems already demonstrate how crucial sound is to presence. When wearing a virtual reality headset, visual detail alone is not enough to convince the brain that an environment is real. Spatial sound provides depth, distance, and direction. Without it, the illusion weakens. Spatial audio systems rely on precise timing differences between the ears, known as interaural time differences, and subtle variations in intensity, known as interaural level differences. When a sound reaches one ear slightly before the other, the brain calculates its direction. Engineers replicate this effect digitally using head-related transfer functions, mathematical models describing how the shape of the head and ears modify incoming waves. In advanced systems, sensors track head movement in real time. As the head turns, the audio field updates instantly. A virtual sound source that was to the left remains anchored in space, just as it would in the physical world. This dynamic adjustment is essential for immersion. Companies such as Meta, Apple, and Sony invest heavily in spatial audio research for consumer devices. Apple's spatial audio platform integrates motion tracking within headphones to maintain consistent sound positioning. Sony's three-dimensional audio technology personalizes head-related transfer functions based on ear shape measurements. The computational demand behind these systems is significant. Real-time audio engines must simulate reflection, absorption, and occlusion within virtual environments. If a wall stands between the listener and a virtual sound source, the system calculates how high frequencies should be attenuated and how reverberation should change. This modelling mirrors the physics of wave propagation in the real world. Gaming provides a clear example of how immersive sound enhances experience. In competitive games, accurate spatial audio allows players to detect approaching footsteps or distant movement. In narrative-driven experiences, soundscapes create atmosphere, tension, or calm. The brain relies on acoustic cues to interpret space and threat. Beyond entertainment, education stands to benefit from immersive sound environments. Virtual classrooms could incorporate realistic acoustic simulations of historical sites, laboratories, or ecological habitats. Hearing the layered soundscape of a rainforest while studying ecology engages sensory systems more fully than static images alone. Augmented reality systems overlay digital sound onto physical space. A navigation application could guide a pedestrian with directional audio cues rather than visual arrows. Instead of looking at a screen, a user might follow a subtle tone that shifts location as they approach a turn. This shift hints at auditory interfaces as an alternative to visual ones. Vision demands focused attention. Sound can convey information while leaving the eyes free. Voice assistants already demonstrate this principle. Devices interpret spoken commands and respond through synthesized speech. Researchers at institutions such as the Massachusetts Institute of Technology Media Lab explore how sound can function as a primary interaction channel. Auditory displays can translate complex data into acoustic patterns. For example, changes in pitch or rhythm can represent fluctuations in environmental measurements or system performance. In industrial settings, auditory alarms communicate urgency more quickly than text. The design of these alerts depends on psychoacoustics, ensuring they are noticeable without being unnecessarily stressful. Emerging technologies are also investigating bone conduction and tactile audio feedback. Bone conduction transmits vibration directly through the skull to the inner ear, bypassing the eardrum. This approach allows users to hear environmental sounds while receiving digital audio overlays. It expands possibilities for safe augmented reality applications. Artificial intelligence further transforms sound interaction. Machine learning algorithms enhance speech recognition in noisy environments. Real-time translation systems convert spoken language instantly, allowing communication across linguistic barriers. The combination of advanced microphones, neural networks, and digital processing creates responsive sound systems that adapt to context. In medical training, virtual reality simulations incorporate spatial audio to recreate operating room environments. The realism supports situational awareness. The sound of equipment, conversation, and environmental cues contributes to decision-making. Even architectural planning may integrate immersive sound modeling. Designers can walk through virtual models of buildings and hear how voices will carry within them. Acoustic simulation software developed by research groups in Europe and North America allows prediction of reverberation and clarity before construction begins. Entertainment platforms experiment with personalized audio environments. Streaming services explore adaptive mixes that adjust spatial positioning based on listener preference. Live concerts transmitted through virtual reality can reproduce the sense of being surrounded by an audience. There is also growing interest in acoustic holography, where arrays of speakers create localized sound fields. Instead of filling an entire room with audio, sound could be directed precisely to specific areas. This would allow multiple users in the same space to experience different audio streams without headphones. The science behind these innovations remains rooted in wave behavior. Interference, reflection, diffraction, and resonance continue to govern outcomes. What changes is the precision with which those principles are applied. As computing power increases, audio engines simulate increasingly complex environments. The difference between physical and virtual acoustics narrows. The human brain responds to acoustic cues instinctively. When those cues are accurate, immersion follows naturally. Future soundscapes may become adaptive, responding to biometric data. If heart rate rises, a system might adjust ambient sound to encourage calm. If concentration wanes, subtle shifts in rhythm or tone might refocus attention. Ethical considerations accompany such capabilities, but the technological foundation is forming. Sound-driven interfaces may also assist individuals with visual impairments. Spatial audio navigation systems can guide movement through complex spaces. Ultrasonic sensors combined with audio feedback create awareness of obstacles beyond the reach of a cane. The evolution of immersive sound reflects a broader shift toward multisensory technology. Vision remains dominant in digital design, but hearing offers unique advantages. Sound surrounds, It conveys distance, motion, and emotion without demanding direct gaze. The future of virtual soundscapes is not about replacing reality. It is about expanding how vibration carries information and shapes perception. As audio systems become more precise and responsive, they deepen engagement and accessibility. Through careful modelling of physics and perception, engineers are crafting environments where digital sound behaves convincingly. The result is not merely an enhancement of entertainment, but a transformation in how humans interact with data, space, and one another. In the end, even the most advanced virtual soundscape relies on the same principles as a whisper in the air. Particles move, pressure varies, the ear responds. What changes is the context. Sound, once confined to physical proximity, now extends across networks and simulations, carrying presence into places where matter alone cannot. Sound began here as something simple, a vibration in air, a pattern of compression and rarefaction moving through a medium. A mechanical wave dependent on matter, shaped by frequency, amplitude, wavelength, and speed. What first appeared as a gentle ripple in invisible particles revealed itself to be governed by precise physical laws. From those foundations, an entire world unfolded. Frequency became pitch, amplitude became loudness, wavelength shaped how waves bend around obstacles and travel across oceans. Resonance revealed that objects prefer certain rhythms, amplifying energy when timing aligns. The Doppler effect showed that motion changes perception without altering the source itself. The human ear translated pressure into electrical signals. Hair cells bent. Ion channels opened. Neural impulses travelled to the brain, where vibration became meaning. The threshold of hearing marked the faintest detectable ripple in air. At the opposite extreme, intense sound demonstrated power enough to damage tissue and structure. Sound extended beyond human perception into infrasound and ultrasound. Elephants communicated across savannas with deep low-frequency calls. Bats navigated darkness with rapid ultrasonic pulses. Medical imaging used high-frequency waves to reveal structures beneath the skin. Seismic monitoring detected distant events through subtle atmospheric fluctuations. Silence, too, proved to be more complex than absence. It became a state of reduced stimulation rather than absolute stillness. Even in the quietest chambers, internal rhythms remained audible. The mind responded to the absence of external vibration with heightened awareness. In space, sound reminded us of its dependence on matter. Without a medium, mechanical waves could not propagate, yet vibrations persisted within spacecraft, within stars, and even within space-time itself through gravitational waves. The universe, though silent between objects, was never truly without motion. Technology transformed how sound is shaped and experienced. Three-dimensional audio simulated direction and depth. Active noise cancellation manipulated phase to reduce unwanted noise. Ultrasound guided medical procedures. Acoustic engineering shaped concert halls and cities. Virtual environments recreated entire soundscapes through digital modelling. Throughout this journey, one principle remained steady. Sound is organised motion in matter. It travels through contact. It interacts with density and elasticity. It reflects, refracts, diffracts, and resonates. It carries energy and information across distances both small and vast. But beyond physics, sound shapes emotion and memory. A melody can recall years in an instant. A sudden noise can alter heart rate before conscious thought begins. Environmental soundscapes influence ecosystems and well-being. Architectural design guides how vibration fills space. Technology extends sound into realms where physical proximity no longer limits communication. Sound is therefore not merely something heard. It is something experienced, interpreted, and integrated into daily life. It informs, it warns, it comforts, it connects. The air around you at this moment is in motion. Molecules shift and collide. Some vibrations reach your ears and become perception. Others pass unnoticed. The acoustic world continues whether attention rests upon it or not. Perhaps the most remarkable aspect of sound is its invisibility. Light can be seen, touch can be felt directly. Sound is sensed only through its effect on matter and mind, yet its influence is constant. It defines spaces, it structures language, it reveals distance and direction. It links individuals across rooms and across continents. It bridges the interior of the body and the vastness of the cosmos. From the faintest whisper at the edge of hearing to the shock wave of a sonic boom, from the rumble of distant thunder to the carefully engineered acoustics of a concert hall, sound remains a dynamic force woven into existence. It is physics made perceptible. It is vibration made meaningful. And perhaps the next time a quiet moment arrives, or a familiar voice carries through the air, there may be a deeper awareness of what is truly unfolding. Not just noise, not just tone, but organised motion travelling through matter, shaped by natural law and interpreted by a living mind. The world does not stand still. It hums, resonates, echoes, and pulses. And within that constant movement, there is both mystery and beauty, carried invisibly on waves that begin with the simplest of motions and ripple outward into experience.